Welcome, hackers! This is Tacit Sanctuary. Have you ever thought about what a digital image is? Of course, it's a bunch of pixels, tiny dots that have some quality of light or dark or color or transparency. If we look at them from far enough, pixels make up images and even videos. And guess what? From the perspective of Uiua, an image is nothing but an array of numbers. So today we will explore how to create some graphics in Uiua and also check out some trigonometry along the way. You may have noticed that even the Uiua logo itself was drawn in Uiua. Let's start with the basics. An image has height and width, so it is a rectangle, in other words, a matrix or 2D array of pixels. How do we create a matrix? The first example is the multiplication table. I use the range function to get the numbers from 0 to 9, then just add 1 to each value. Now I make a copy, and I can combine these two arrays with the table function. Each value from the first array is paired with each value from the second array, and I need to supply a function how to combine the values. For the multiplication table, it's this simple. It's important to note that we can combine arrays of different sizes, so the result can be not only a square but also a rectangle. Now we can observe that the first array is used for rows and the second one for columns. Also notice, with addition as the combining operation, I have the same number in the diagonals. I can use more complicated formula for creating the table too. And check what happens if I start with big enough arrays. When we have more than 30 values each direction, the online pad automatically converts the matrix to an image. I can still inspect the actual numbers with the %p command, which is used for printing to standard output. Because of the function I used, each number in my matrix is between 0 and 1, and they build a nice repeating grayscale gradient. 0 is black and 1 is white. I can increase the size of the image or modify the stripes using different numbers in the formula. I can also try other transformations. With reverse, I mirror the image across its horizontal axis. With transpose, I mirror across the diagonal. To create a plot, we typically want to inspect each x value along the horizontal axis and find the y value that goes with it after we apply a function. From the resulting points, we build some kind of line. Let's have a look at the easiest possible example, the identity function. So starting from the same horizontal and vertical ranges, I want to mark the x values which are equal to y. So I use equals as my table function. And I get a nice straight line indeed. The only problem is that it goes the wrong direction, and that's because my values are growing from top to bottom. But reverse is an easy fix to get the usual arrangement for my graph. Now we often don't want to start counting at 0, and we even want to work with different ranges for the x and y axis. Also, I don't want to hardcode the specific values, but I want the program to dynamically create as many values as needed, in case I need a smaller or bigger picture. So let's build a function that takes 3 arguments: the number of values, the starting point, and the ending point of the range. And it should generate an evenly distributed array of numbers. This is going to involve some juggling with the values on the Uiua stack. Let's say I want 5 numbers between 40 and 60, including the edges. I want my result to be this array: 40, 45, 50, 55, and 60. So I have to calculate several things: the difference between the start and end values, I kind of need to divide it by how many values I want, with a little adjustment. This will be my increment. I can multiply the increment with a regular range that has just as many numbers as I want. And finally, add this to the lower end. How to code this in Viva? Keep in mind, I have 3 values on the stack now. These are my arguments. I want to calculate the difference between the second and the third one. I can do it with the dip modifier. Dip jumps over one value but keeps it on the stack. Luckily, the boundaries are in the correct order, the result will be positive. But this operation consumes both numbers, and I actually want to retain the smaller one for later. So I use a fork here and put identity at the end. Hence, I can do several things on the same arguments at once. The next job is to calculate the increment. If I do a division now, this would be fine if I want to exclude the highest value of the range. But to include it, I actually have to subtract 1 from the number of values. Now I have my increment, but I face the same problem as before. The n argument was consumed, and I actually want to create a range from it right now. So again, I can use a fork, just this time I need to use parentheses because my subfunction is more than a single glyph. Finally, I multiply the range with the increment and add them all to the start value. I can assign this to a name and test my function with different values too. It is now time to create our ranges for the x and y axes. I am going to plot simple trigonometric functions, sine, cosine, and tangent. Actually, Viva does have some built-in constants that help dealing with circles and trigonometry. We even have 3 different ones that are related to each other: eta, pi, and tau. Viva is just trying to play nice and show us the formatted symbols in the code when possible. Again, we can use the print command to see their float value. Eta is the half of pi, and tau is the double of pi. The values of sine and cosine can range between -1 and +1, but for the sake of tangent, I will make the scale up to 2 and use the height of 100 pixels. To get a good view of the plot, I am going to use 250 values on the x-axis between minus and plus tau. Since we are providing all the parameters up front, it makes sense to turn this function to a compile time constant. This way, we make sure that even if we use them multiple times, they are only ever calculated just once. So this is an optimization technique. And this comp time modifier does not have a glyph either, so the formatter just leaves the full name there. Now we have all prerequisites to create our first real plot. Let's put our x and y values on the table. Apply the sine function on each value of x. As you would suspect, this function needs numbers in radians. Then we can compare the result with the table equals. The reason why we see only darkness is because most of our values are going to be floats, so equality is not really efficient here. We can come up with a formula that compares the difference of values within a margin of error. So I compare the absolute difference with an arbitrary number. I have chosen this because it looks good on this particular graph, but we should adjust it if a different scale is used. Now we can see the line, but the shape of the graph is funny. After applying the sine function, I can flip the arguments. Remember, the first one will control the number of rows, so that should be the y-axis. Also, I need to reverse the rows at the end, so that the numbers on the y-axis are increasing from bottom to top, as we are usually looking at our plots by convention. Now this really looks like a sine plot. To make it reusable, I am converting this to a macro, where I can pass a function to it. So I can use the same code with different functions. The number of exclamation marks in the macro name. Note how many functions it can take. And I use the placeholder in the macro body to execute those functions. Also, the x and y coordinates can be dynamic here, rather than being hard-coded. Basically, I have written my own custom modifier that works similarly as partition or reduce, just like higher order function. I can immediately try the cosine function. Even the documentation of sine is helpful to point out that even though cosine does not exist as a separate function, but trivial to derive from sine, because we just need to shift the x-axis by eta. Finally, calculating the tangent is a little more laborious. But based on our trigonometry studies, tangent is actually sine divided by cosine. And again, the documentation is helpful enough to provide an implementation of this function. If you enjoy code golfing, you will also find it interesting to examine a different version on the Uiua page. That is only 4 glyphs. And now we have 3 beautiful plots of sine, cosine, and tangent. A plot feels a bit incomplete without showing any axes. We won't have a lot of sophistication here, cannot exactly do what matplotlib can do in Python. But based on how I chose my ranges, for this particular example it would be sufficient to draw a straight line in the middle, because the low and high end of the range is the same. So that would put the line at the 0 value for both axes. Let's see how we can do this just for a single plot at a time. First, I want a black canvas with the same size as my actual plot. So I make a copy and I take the minimum with 0. This is a pervasive operation and very efficient, and it will replace every positive number with 0. Now I will draw a horizontal line in the middle. After making another copy, I use the length function to find out how many lines we have total, and then take half of that. Round the result just in case we want to work with uneven rows at some point. So this number is the index of the middle row. I can use a structural under pick operation to temporarily restrict working only on this row, and similar to my previous trick, now I use maximum with a number that represents a dark gray shade, just to make the axis fade into the background. Now I have the original plot and another one with the same dimensions, but with the horizontal line. Guess how I can combine them? Taking the maximum of the two plots, we use the higher number that represents the brightest color from each plot. It's pretty cool. Now I can convert this to a function as well, and use it 2 times. Once normally, and the next time on the transposition of the plot with the under modifier to rotate it back to its original position after adding the line. There are multiple ways to represent a colored pixel, and this time we will use the RGB red, green, blue method. So right now the shape of our plot has 2 dimensions. In every intersection sits a pixel represented by a number between 0 and 1. This is a grayscale image. To make it colorful, we need to have a triplet representing each pixel. Again, the 3 values will range from 0 to 1, representing the quality of red, green, and blue. We can of course mix and match the colors in any float ratio. For example, 101 contains only red and blue, and hence it makes a full purple color. So to paint our graphs, let's multiply each value in our existing plots with a different color. Now we can observe with the shape function that the rank of our array has increased to 3, and the last dimension has 3 values. Let's combine all of them to a single plot now, as finally we can determine which line is which function. Using the maximum function twice will do the trick. And adding the final touch with the 2 axes, this still works even with the colored version. Drawing images this way is truly one of the differentiating features of Uiua. I am sure that some libraries will eventually emerge to make this process easier, but even with the built-in functions we can achieve a lot. I really recommend to check out the showcase channel of the Uiua Discord server. Many Uiuans often post their very interesting creations, and I even used some of those in my intro video. If you enjoyed this content, then don't forget to like and subscribe to my channel to help it grow. See you around next time.